All right, so hello everyone. My name is Valerio and I'm an open source developer with that and also contributor to the Skupper project. So today I have organized my session in two main parts. Well, the first part is just one slide. We will start a quick look to Skupper and I'll explain you what is in one sentence and I will highlight three keywords that capture the main idea of what is it Skupper. So in the second part, instead, we are going to explore the idea of Skupper more closely. I'll take you through the common problem of multi-cloud and we will try to understand how Skupper helps us to solve this problem. Okay, so let's start with this definition. So Skupper is a new approach to connect heterogeneous application through high-level multi-clouding routing capability. What is it, this thing? So what this word means? So when I mention new approach, it's because we are taking a different direction to attack the challenge of the multi-cloud. High-level multi-routing is our method for navigating complexity. So we are using layer 7 addressing the routing approach to connect services. And when I say heterogeneous, it's not just talking about Kubernetes. We are extending our, reach to devices and platform. So let's consider that as a solid starting point to connect the dot in our exploration. And fortunately, so the first part is finished. So now let's kick off in the real conversation with a few questions. Why multi-cloud is a buzz today? So why organizations are moving toward multi-cloud and how it affects people, how it affects your organization experience or your developer experience. And I think we should start from the high level, from the business goal driver. So, for example, imagine an online shopping that you can automatically increase its server capacity when many people are visiting the store. And when the demand decreases, it scales down, saving resources. Consider the scenario where you are an hospital and you need to keep safe patient medical records. So probably you will keep these data on premise. Productivity. So your marketing team and your organization can use cloud services for data analysis, while the development team at the same time use cloud provider resources for different stuff like software testing and development. So clearly, multi-cloud applications are gaining, momentum. There is a good reason for that, but let's bring us challenge. If you look at how big applications have changed over the time, it's like they are constantly moving and evolving. In the past, there were mainframe server, then we started opening up the application stack, placing them inside a virtual machine. Later, with the rise of the containers and orchestrators, such as Kubernetes, we gradually moved away from the virtualization. In conclusion, we are moving data among different platforms and devices, and that's what we call heterogeneous application. And the challenge here is that moving data from a chaotic infrastructure and transform that in homogeneous, safe place. And that's in general, but from my perspective, your perspective, from the perspective of the developer standpoint, let's explore this challenge from the direction. Now, for the upward arrow part, we already got some solid solution in place. Let's think about container like OpenShift. They allow you to work with different Kubernetes flavor, but from the perspective of the application change, there is a consistent and current way of working for developer, and without changing any line of code. And that's mean homogeneous. We can say, we pass from replatforming an application to redeploy an application, which is an improvement. Sadly, today, it's no longer just about installing and configuring your virtual machine as an administrator, moving data back, shifting from a platform to another platform, and stop, repeat. There is more. In fact, if you take a look to the horizontal arrow, we still don't respond to the same important question. How best link my traditional application and infrastructure with my greatest Kubernetes apps? How we do move a workload from a cluster 1 to a cluster 2 efficiently? That's the second. How do we interconnect application across different Kubernetes clusters? These are the questions that we try to solve. So let's start, take a look to the last question, briefly analyzing some common tool and platform that probably you already know. Okay, so the connection between two Kubernetes services across different cloud and using IP addresses, can be technically possible. But this is implied that services will be directly accessible from internet. Of course, this introduces security risk. So we need strong security roles and monitoring to keep everything in check. Furthermore, it's true that you can access from a private service to a public one with the NAT, because the NAT keep the translation of the address in memory. But that's not the contrary. You can do port forwarding if you want, but it's like expose the services internet. So we are in the same start point. VPN and gateway solve this problem, but the larger is the network, the more complex they become to manage. So for example, during the NAT configuration, if there is an error in the IP address transformation role, it could lead to translating an IP address of a cluster A into an invalid range of the cluster B or vice versa. So the result in the end is that nothing works anymore. Another problem is that VPN require administrator privileges, so leading to delay, administrative overhead, and mobility issues. What about service provider? Service provider also perform network isolation as well, but here a couple of challenges. One is the vendor lock-in. So the vendor lock-in happens when your application depends on proprietary technology, and it means that changing provider becomes painful and costly. And that's especially true for my experience for a database and API layer. But the big downside is the cost. The cost of the connection may be not trivial. So providers charge fees for public and private communication or data migration, making things big pricey. So now we started to see something more interesting. So this is an example. So take for instance a data aggregation architecture, say, so they collect environmental data from sensor or generated events. So this sensor could be a number of thousands, and they transmit information to the collector, and then this information are summarized in central back office for something stuff, analytics, let's say. But what is important note in this picture is that the collector themselves can be distributed outside the public internet. For example, the central one could be at the edge. So I really don't want to configure each individual devices to reach its collector, especially if one of them is moving from left to right. That's another problem. There is a kind of mobility issues here. For instance, a sensor might be on a truck that travels across the country and change position continuously. How the hell? No. Now, recap. From the previous slide, I think we can deduct where is it the challenge, at least in terms of layer stack. Here, looking to this weird arrow, I think we can understand what the challenge we need to face. And now it's a scary moment. I don't know if go to the next slide because I have to do, some sort of big statement. So the problem is there. So the internet protocol is not suited well for hybrid edge and multi-cloud interconnect. I give you another example. Think about a video surveillance. So I'm here in London and I want to see what happened in Spain there. So a direct communication. But the reality, what is it? I have to open my application, I have to log into a server, so the server then asks information to my video surveillance, send a response, and then I receive the response. So it's not a direct communication between me and the video surveillance. I have to use another thing, I have to use another server. The hard fact is the IP is built from client-server world, which is vertical communication. But today, it's not sufficient because applications need to communicate in all directions and services are located everywhere. We saw before, We want to add or remove resources, we want to migrate data from different locations, we want to distribute the load. So communication are not unicast, so anycast and multicast communication are predominant. You can do global multicasting IP, and my technical and professional response is good luck. To summarize, we are trying to adapt our architecture with the network infrastructure and not for business goal. That's important. So what's the idea? The idea is providing an high-level functionality to prevent asking the network layer to perform tasks for which is not intended, like global multicasting. I'm sorry, I don't like global multicasting to IP. And the goal is allow network layer to focus on its core strengths, such reliability and maintaining strong communication capability. And here we are. That's why we created the VAN, the Virtual Application Network. The VAN is a middleware that lives between the network layer and the application layer, and that brings about several advantages. For example, it simplifies the understanding of the communication between services and allow to remove and update them without modifying the network configuration. And also thanks to that, we also have a scalability benefit because when a new service is added, no? But most important, services can be distributed among clusters independently of their physical location, which is crucial for a heterogeneous environment system. So now, let's go into the specifics of what this technology should be capable of doing. And yes, most of them are, like a service mesh stuff. First, we are changing the way we conceptualize addressing. So in the classic TCP/IP, what's happened? So in the classic TCP/IP model, a name, an URL, so is mapped to the host address through the DNS server, and the host then address direct the host, and then you carry the port and you can find the target. In our case, names are addresses for routing messages, and these names are services. That means that we are routing towards services rather than hosts. VAN is a multi-access technology, meaning that multiple services are expected to be distributed using the same address. And this is precisely what we aim to achieve. No? We want to have multiple instances of the same service for purpose of high availability in case one of them fails. We want to distribute the load among different instances of the services. Or maybe we want a location where one service is managed Asia and another Europe and so forth. Now we start the technical part. So let's explore what the VAN can do for us. So we can divide the VAN into two phases, the bottom phase and the top phase. So on the bottom phase, with the VAN, we oversee the connectivity among devices and cloud environments. So we introduce the concept of site that serves as a container for a portion of our application. And because we are not working at layer 3 anymore, this approach eliminates the need of firewall and VPNs. The router-to-router communication uses MTLS with a dedicated certificate authority, which is very locked down from the standpoint of the security. And all ports that not use MTLS are closed by default. And the only time the application open a port at the public is if actually wish to do that to connect an ingress or a website. We also provide the redundant topology, so there are no full mesh here networks, but we have the flexibility to tailor the degree of redundancy to suit our specific requirement. So Sydney can communicate directly with New York, but if the link goes down, there is a secondary path that you can follow. We also provide. Oh, okay. Sorry. I was anticipating some concept. The other important thing is the application don't need to be modified. That's because we already implement protocol like HTTP, HTTP2, gRPC, JDBC. So the application is already for these kind of things. We natural fit into Cortelia platform. We say before we use Kubernetes. You can use Podman. You can use ARM64. And the other point is a lightweight. So basically, most of the code is written in C, so we have a very, very low memory footprint. And also the library that we are using behind the hood are for IoT services. So in case we have IoT devices or memory constriction, Skupper can be a good solution. And so, okay, so let's explore another time here what the van can do for us. So you see, on the bottom face of the van, we oversee the connectivity, and we say before. So we see also the router-to-router communication, and also we provide topology redundant. The part that's missing is this one. So as we move up, the infrastructure disappears. And the only thing you can see is how the application is connected. And each service thinks that we are talking in localhost. No? So you see 2 Redis instances running on the same address, and maybe they are deployed into different countries. And so what we do, actually what you do at the van level after the application has been deployed in the site is to create service links that enable 2 or more processes to communicate with each other. Now, do you remember the example that I did before about the sensor, etc.? So now, if we suppose that this application run in a Skupper network, and we send a post request like this one to a sensor, so the van automatically direct the request to the collector, best suited to handle that. And we don't need to change any configuration, even if the sensor change location, because the address is the same. So now, more or less, we have all technical concepts to define a Skupper. And define Skupper at this point, it's very, very easy. So Skupper is an implementation of the virtual application network. Or if you prefer, Skupper is an open source tool for creating virtual application network. Actually, I don't want to spend a lot of time on this slide, but you can think about Skupper in 3 big blocks. One is the data plane, is the router data plane, and because we discussed before about the van, I don't think I have to add any other kind of informations. Regarding the control plane, so we handle the communication between router. As you can see, there is integration. It's handled the integration between Docker, Podman, bare metal, other stuffs, and so it's create a distributed application running across namespace and also handle the policies. We have also a part related to the observability, mine, where we gathering information from the router, we manipulate this information from the router, we have an internal database, plus this information are sent to Prometheus to do some sort of availability that will be read from the console. More or less, this is what we have at the console. As you can see, we have topology stuffs, infrastructure level, also application level, and we do some sort of basic monitoring, I can say. Latency, request, response, and byte rate, so the normal stuff. Actually, this is not important for our conversation, but it's my moment of glory, so I just want to share this, this slide. Okay, so now, at the end, we want to see the workflow, because it's very easy. Doesn't matter if you are in a big project or not. Let's say we have 2 namespaces. So one in London, one in Sydney. So the first thing we have to do is create this namespace. The second thing is doing Skupper init. At this point, you do 3 things. You install the router, you install the controller, and then you create the config map, so the site. So the site, we know now that it's a config map. The first thing is we have to start to create a link. No? So this command tells to Skupper to generate a secret token file on your current machine with this information about the links that we are going to create and certificate that grant the permission of other instances. So there are two types of token that it's possible to create. One is this one, is the claim token, which allows you also to specify the maximum number of uses by other sites and a valid period. The third token instead is just a permanent that not expired. So from a side, we create the token, and the token is in our file system. So at this point, we switch the namespace and we go in est. And so at this step, complete the connection and tell to Skupper to link another site, providing a secure router-to-router communication. Because we saw before, we have a certificate. Now things are a little bit more interesting. So we just saw before that were the step to build the network technology, the network topology. Now it's time to connect our application at the service level. And we can achieve that doing this command, expose. We expose a service. So what is interesting to note here is that a proxy service, so the red block, no? The proxy service is the service that we expose, and here it's in the west side. So that's the reason why if the front end send a request to the back end, it thinks that the communication is on the same host. Now, if you are in the west and we take a look to the pods and the services, we see something interesting, no? So we have the Skupper router, we have the service controller, and we have the front end as expected. But if you take a look to the services, we have this backend, which is what we said before, is the proxy. And I want to go a little bit more in deep, and that's the magic of everything. So if you take a look to the service, we see that the selector is the router. So what's happened? I'm the front end. I send a request to backend 8080. So the local proxy gets the request and then forward this request. But this request is intercepted by the router, and the router in the van say, hey, where is it, the real backend services? Oh, it's there in Nest. Go there. And that's how it works. That's how it works. Now, I would like to come back to the origin, to the challenge at the beginning of this talk, and respond to the question that we have seen before. You know? And to make this example more tangible, imagine, imagine a monolithic web application that has already been refactored into microservices. So we want to migrate this refactored code from a local machine to a public cloud. Just one note. This is a scenario that I simplify, but in reality cover real use cases we had, such as moving to a cloud or migrating from different versions of OpenShift, like 3 to 4. And so the first things we'll do is deploy a Skupper gateway locally to the traditional application and a Skupper router to the cluster. So for our point of view, the Skupper gateway do the same things of the router. Actually, it's a little bit different, but I don't think it's important for our workflow. So at this point, I can start moving the microservice we have created from a monolithic application to the cluster. And what's happened here is that if a service A needs to talk with the web application or even with the DB, it's just talking locally. And the router is going to intercept the call, or if something in the web application want to call something that was refactored in the service, it's going to hit the gateway. Then the second step, we move service A and service B in the public cloud. And note that they live in a cluster 1, a proxy of them. So when the service C needs to call the service A, still it thinks that the service is there. And if the service A wants to communicate with the database, the communication will be router and then gateway. And so I think we have responded to every question. Just as last slide is something that it's for the future, for the direction. So we are working on this project called Skupper X, and one of the main points of Skupper X is the ability to manage and monitoring many separate virtual applications from a central point where other one can require and get a grant to join in the bigger network. No? So the current Skupper that we see here is focused on the application owner. But in enterprise grade company, you need also to separate platform administrator and own persona. So that's what we do. And the second point is related to the declarative model. So honestly, we saw before the CLI, but we believe that we should not interact in Skupper with the CLI, because the real operation that developers do is deploying stuff. So with this approach, we want to let to the developer to deploy their site, topology, connection, services, whenever, just doing a normal deploy of a YAML file. And I think I don't want to elaborate anymore, so I finish my talk.